Hi, thanks for joining me. Today we've got a very interesting matrix problem. We have a matrix A which is n by n and it has the property that a cubed equals 0. We want to solve, or in other words, find matrices X which satisfy X plus AX plus XA squared equals A. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so if we do have a solution to this equation here, X has to be an n by n matrix, and that's because A is n by n, A squared therefore will be n by n, and here you can see we're post multiplying by X, and here we're pre-multiplying by X, so X would have to be n by n for both of those to be like actual matrices. So X is n by n, but this doesn't tell us if there are any solutions to this equation, and even if there are solutions, is there one solution, is there finitely many solutions, are there infinitely many solutions? We don't know just yet. And also what makes this problem tricky is the fact that these matrices don't necessarily commute. So I can't write this xa squared as a squared times x or something like that. And of course these are matrices, so I can't really divide by matrices. I can multiply by inverses, but it's not quite clear what we're not told if A is even an invertible matrix or not. But we do know that A cubed is 0, so in fact that will tell us that A isn't an invertible matrix. So A cubed is 0, so that's the main fact, and this thing here. So we want to see if we can use the fact that A cubed is 0. So when we stare at this equation here, it's very tempting to multiply by A, so post multiply by A, because then this A squared here will become an A cubed, and then this term here would vanish. So we think about that and we go, well, let's see if we can do more than just getting rid of one term. How many terms can we get rid of? So the first thing I'm going to do is just rearrange this. So I'll just keep this x on the left hand side. So again, I'm going to get x equals a minus ax minus xa squared. And now I want to see how many terms on this right hand side I can get rid of. So I noticed that, well, because a cubed is going to be 0, what I can do with this left hand side is just pre and post multiply by a squared. So this thing here, at least as of yet, doesn't have any a cubes in, so this thing here is still going to just be by itself, it's not going to vanish. But if I pre and post multiply every term here by a squared, so if I do this, what's the first term going to be? A squared times a squared is a to the 5, but that's also going to be 0, because if a cubed is 0, a to the 5 has to be 0. It's going to be a cubed times a squared, so 0 times a squared, so 0. What about this middle term? Well, that's going to give me minus a cubed x a squared. Look, I have an a cubed here, so it's going to be 0 times some matrix, so still 0. And this last term here is going to be a squared times x times a squared times a to the 4. So minus a squared x a to the 4. But a to the 4 is going to be 0. So each of these terms here are going to be 0. So I've worked out that a squared times x times a squared has to be 0. Which, who knows whether that's useful or not just yet, but I found a matrix that equals 0. So if there is a solution x, then it must be that a squared times x times a squared equals 0. Well, what else can I work out? Well, let's go back to this equation here and just look at pre-multiplying by a squared. So up here we did it with a squared at the end, but let's see if we can just pre-multiply it by it. So if we do that, we're going to get a squared times a, which is a cubed, so that's going to vanish in a moment. This next term here is going to be a cubed x, so that's also going to vanish because a cubed is 0. And then the last term is going to be a squared x a squared. So this thing here is 0 because it's got a cubed in it, this thing here is also 0, and this thing here is minus a squared x a squared. But have a look at this. We just proved that this has to be 0. So a squared times x also has to be 0, which is quite nice. Okay, and you can see we've gone from a thing with kind of 5 terms in it, 4 a's and 1 x, to something with 2 a's and 1 x in it. So hopefully we can keep doing something similar and see if we can just get x by itself on the left hand side and some expression on the right hand side. So let's now consider, let's say, a times x times a. And again, going from this equation here, so pre and post multiplying by a. So if I just write it out, the first term is just going to be a cubed, so that's going to vanish. And then I'm going to get minus a squared x times a. And then I'm going to get a times xa squared times a cubed, so minus a xa cubed. So this term vanishes because it's got an a cubed in. Same with this one, it's going to vanish. And then this term here has got axa in it. Oh, sorry, it's got an a squared x in it. and we just showed that a squared x is 0, so this bit here is 0. So overall, this is also going to be 0. So we found another matrix which is 0, a times x times a. And we're going to see if we can find any more. So we've considered a few different possibilities. And now you might ask, well, are we just going to keep doing this forever? Keep considering different, matrices? And the answer is no. There's only going to be finitely many. In fact, there's going to be at most 9, because we can have x in the middle, and then how many a's can we have on the right hand side? Well, we can either have a to the 0, a to the 1, or a to the 2, because we know if you have a3 there, that's a to the 3, that's going to vanish. And similarly on this side, so there's 3 choices for the exponent of a on the left of x, and 3 choices for the exponent of a on the right of x. So that's going to give us a total of 9. So the next one we're going to consider is x times a squared, so a squared on the right. And now what is this thing here? Again, we're just going to go from this thing here and post multiply by a squared. So we're going to get a times a squared, which is a cubed, minus ax a squared, minus xa to the 4. A cubed is 0, a to the 4 is 0, axa squared, that has an axa in it. So this thing here is also going to be 0. So we found a bunch of matrices so far which are 0, and you can kind of see, like, now we've shown that xa squared is 0, we can kind of get rid of this term. So we have that x is equal to a minus ax, and now it becomes a little bit simpler as to what we're considering, and to help us try and work out what x is. But let me clean up the whiteboard and we'll continue. Okay, so we've just proved that all these matrices up here are 0, and we have this thing here, but we've just proved that xa squared is 0, so in fact we can ignore that term as well. So we have that x equals a minus ax. The next matrix we're going to consider is ax, so we're going to multiply both left and right, or pre-multiply both sides by a, so ax equals a times a is a squared minus a squared x. But a squared x from this thing up here is 0, so this is just a squared. So we get ax equals a squared, which isn't 0, or might not it's not necessarily 0, we don't know. We only know that a cubed is 0, but it's still useful. We've got that ax equals a squared, and what's quite nice about this is we don't have x anymore. So we know that a times x, regardless of what x is, provided it solves this equation up here, then a times x has to be a squared, and a is a fixed matrix, which has the property that a cubed is 0. Okay, so if ax equals a squared, well, we can just plug that into here, and so we get an equation for x. X equals a minus a squared. So what have we done? We started with this equation up here, and we also had the fact that a cubed is 0, and then we just played about with this. So we said if x satisfies this equation, then a squared x a squared must equal 0, a squared x equals 0, and so on. We got all these equations here, and it boiled down to this thing here. So essentially, if x satisfies this equation here, then x must be a minus a squared. So what does this tell us about this problem? This tells us that if there is a solution to this equation, then this solution is unique. In other words, the solution must be x equals a minus a squared. Now, how do we know if this is a solution or not? The easiest way is just to plug it back into here and check that it all works. So let's plug it in. So if we plug in x equals a minus a squared, what do we get? We have a minus a squared plus a times a minus a squared plus a minus a squared times a squared equals a. So we're basically checking if this is true or not. So let's just go ahead and expand. So we get an a here minus a squared plus a squared there. We're going to get a minus a squared, but that's going to be minus a cubed, so that's going to be 0 anyway, so we can ignore that. Then we're going to get a plus a cubed here, and then minus a to the 4, so those terms are both going to be 0, and then this is supposed to equal a. The minus a squared here is going to cancel with the plus a squared, and we're left with a equals a, which is definitely true. We can just kind of reverse the steps. It's an if and only if kind of thing. So that tells us that this is indeed a solution. So therefore there is only one solution to this equation here, namely x equals a minus a squared. I hope this solution has made sense, and I hope you've enjoyed this problem. This one comes from the International Mathematics Competition, I believe the 2021 competition. Anyway, thank you for watching. I will catch you in the next one. Have a great day.